This is an example of problems that are like problem B2 in your work. Use the 0.01 significance level to test the hypothesis that full-time desk employees who work at home put in a different number of hours actually working at their jobs than people in general. The sample, n equals 35, had a mean of 42.5 hours per week. The average mean for the population was mu equals 40.2 hours per week. Standard deviation 5.2, normally distributed. So let's begin by parsing the problem. What is the population that's going to be a little bit different? And what I see is this: full-time desk employees who work at home. Full-time desk employees who work at home. And we'll be comparing them to full-time desk employees in general. It states up here people, but I know that we're talking about the same individual, the same type of person. So I'm going to state this more clearly. We're comparing full-time and desk employees who work at home with those in general. We only want one difference between the groups. And I know that's what this problem is intended to say. So what are we measuring? We're measuring the number of hours actually working at their jobs. You maybe know that some computer programs will do this, monitor the exact number of minutes you're working by your eye tracking devices or looking at what is on your computer screen is kind of creepy, I think. But number of hours working at their jobs. So actually doing work on their computer that's relevant to their jobs. We're looking for tails. I'm looking for words like lower or higher or different. And I see our word different right here. I know that we're looking at then a two-tailed test. Not sure what I just did there, but let's type that in properly. And the research hypothesis, I think it says that pretty clearly right here. So I'm going to copy that and see if I can adapt it to this. So full-time and desk employees who work at home put in a different number of hours. I think I'll add the word will, because this is a prediction, put in a different number of hours actually working at their jobs than people in general. I'm okay with that. I think I'm going to change this to full-time desk employees. All right, and then for the null hypothesis, I can just type in, I'm just going to copy the text this time so I can keep the yellow. Full-time desk employees who work at home will, and I'm going to add up here in the function bar, formula bar, this word not put in a different number of hours. Now we're on to step 2, the comparison distribution. I know that the center will always be mu. The spread will always be sigma to the distribution of means, and the shape is going to be normal. But let's go ahead and tease out the data from this problem. So the first thing we need is n, and I can see n is 35. Next, we need m, and that's the sample mean. And I can see right here, the sample had a mean of 42.5 hours per week. So I'll write 42.5. Next, we need mu. Here we have the mean for the population was mu equals 40.2. So I'll put 40.2. Next, we have sigma, and we're given sigma 5.2. And we'll have to continue because we need the standard deviation for the distribution of means as representing the center in this distribution. So we'll calculate the variance using our formula of standard deviation squared. So let's click on standard deviation and square it. I know that the formula for the variance for the distribution of means is variance divided by n. So we'll type equals, click on variance, and divide by the number in the sample. Hit enter. And then I simply need to take the square root of the variance for the variance to get the standard deviation for the distribution of means. So equals square root and I'll click on the variance for the distribution of means. This number, 0.87896042, is the spread in this example. I could write this as this sigma to the distribution of means. I find it easier to just write SE for standard error or SEM. I'll put that because we're talking about the distribution of means. So SEM equals 0. I'll round to 4 decimal places, 8790. And that's because I rounded the 89 up to 90. And that is the spread. The center is just going to be mu all the time. So the center, I'm just going to write mu equals, and it's 40.2. And the shape, it's going to be normal. We know this in particular because we have more than 30. So that's, if it wasn't stated, I could still feel confident. It was stated, and that's what we should assume for our problems here. Next, we have to determine the cutoff point. For that, we need alpha and tails. We can see that it's two-tailed, and we need the 0.01 significance level. So let's get our critical value calculator and take a look. We'll change this to 0.01. Enter. And we can see that in a two-tailed test, our cutoff point is plus or minus 2.58. I think I'll just copy this to write this down. Our cutoff point is plus or minus 2.58. If you don't want it to change font like that, you can just right-click and click on that, and it will paste that volume. And now it says mark this on the graph to the right. So here we have a graph, the sample size n equals 35. I'm going to fill this in for the title. And if we scroll a little further, we should put down what our z-scores are for. And these are going to be z-scores for, we already said it's distribution of means, but what is it we're actually measuring? In this example, our dependent variable is numbers of hours working at jobs. Numbers of hours working. And I'll put actually, because that's not just going to work, but actually working at jobs. There, now I've got things labeled. That's always helpful, so remember what we're doing. Our cutoff point is going to be plus or minus 2.558. And so here's our 2. It's going to be way the heck up here. Our cutoff point, 2.58. Way down here between the 2 and the 3, minus 2.58. And I know that the area that's our critical region is, let's make sure I have a nice fine marker here because it's so tiny, is this region and this region. And we'll call this our reject region and our reject region. And in the center, we know this will be our fail region. So let's go ahead then to step 4, find the sample z-score. Let's calculate that. We know that in this example, z is going to equal our sample mean, because that's what we're comparing now, not just a score, minus the population mean mu divided by the standard deviation, not for the distribution of individuals, because we have a mean here. It's for the distribution of means. And so let's type in that formula. Equals, parenthesis, let's get our m minus our mu divided by our SEM. Not our variance, but our SEM. So let me, and we can't select it here, I see. So let me get cell. When this happens, you can just put its reference points, which is F15. It happens because our formula is too long. So F15. I'm going to change the 14 to a 15 up in the formula bar and hit enter. And then I'm going to check that because we had to do it a funny way. We have the correct cells highlighted. The blue is M, the red is mu, and SEM is the purple. And so that is a correct answer. So 2.62, I think I'll slow it to 2. So Z equals 2.62. And then it says in red, mark this on the graph. So let's mark our 2.62 using a different color here. I think I'll mark it in our sample in red. 2.62 is going to be somewhere up here. This is M equals 2.62. And I can see here, going to our next step, let me write our Z in here, Z equals. And I can see that our decision then, because our score is in the tail, it's going to be, it's in the reject region in the tail, and we'll write reject. I'll just write HO here, reject the null hypothesis. If we reject the null hypothesis, we cross it off and nothing is left but our research hypothesis. So I'm going to copy this down to use in our concluding statement. So here we go. And I'm going to add a little bit of extra, reminding us that evidence from this study suggests that, and there is our hypothesis. We're no longer predicting, so let's get rid of that word will. And let's add the statistic before the period. We're going to put in Z, and then in parentheses, it's going to be 35. And we put the Z score 2.62. Then it's significant, so we write out the probability with alpha. P for probability is less than 0.01. So a very strong finding, even though it doesn't look like much. We'll enter, scroll back to the top just to be helpful, and we're done with this problem.